Section: Introduction. In this section, we delve into the concept of building a library of skills learned in context, represented by RNN states that can be utilized for retrieval and blending. To achieve this, we utilize a set of straightforward tasks proposed by a previous study, where each task consists of a sequence of examples. We leverage a pre-trained Mamba model with 2.8 billion parameters to generate these skills for the library and subsequent testing. Each state representing a skill is derived by processing 32 examples. For each task, we gather multiple sets of examples, resulting in multiple RNN states for each skill. For more detailed technical information, please refer to the appendix. With this setup, we aim to address three main questions. Firstly, can we retrieve the corresponding state from the skill set given a short task example? Secondly, is it possible to blend different states to enhance results? Lastly, can we apply blending to sequential data effectively? To tackle the task retrieval aspect, we analyze the intermediate layer from each state in our skill library and project it to 2 dimensions using t-SNE. This process leads to a clear clustering, where states related to the same task are grouped together. Interestingly, even tasks that the Mamba model struggles to learn are clustered together, indicating that the essence of a task can be decoded from the state vector. To quantitatively assess the model's retrieval capabilities, we check if a query vector obtained from processing a few examples from a task in the skill library can be correctly identified as belonging to that task. Our results demonstrate that our approach can reliably identify the correct task even with a low number of examples, such as 1 or 2 shots. Moving on to state mixing, after confirming that relevant state retrieval is achievable, we aim to enhance our model's few-shot performance using the task library. To blend the states, we simply calculate the mean over them. In our initial experiment, we compare standard in-context learning with mixing. The baseline scenario involves the model processing a single sequence of examples, while our mixing strategy combines states obtained from processing multiple examples independently. We observe that mixing these states can lead to improved performance, especially when using mixtures of states from different tasks. Additionally, we conduct preliminary tests by blending states from distinct tasks, resulting in intriguing outcomes that warrant further investigation. Section Summary. In this section, we explore the concept of state soups, which involve building a library of in-context learned skills represented by RNN states for retrieval and mixing. By using a pre-trained Mamba model with 2.8b parameters, we generate skills for the library and test their retrieval and mixing capabilities. Through tasks like task retrieval and state mixing, we demonstrate that our approach can reliably identify tasks even with low-shot examples and enhance model performance by mixing states from the library. Section: Mixing with sequential data. In this section, we experimented with mixing sequential data. We realized that in practical situations where data follows a specific order, like in processing long sequences, the order of mixing matters. To address this, we developed a mixing strategy that considers the sequential nature of the data. We represented a single layer processing a sequence x_1, L dots, x_t recursively as a function that depends on the previous elements in the sequence. This function can be broken down into smaller parts, allowing us to process subsequences independently and then combine them using a computed matrix. This matrix is crucial for efficiently training different architectures of the model. We named this approach a decay mixing. When using a decay mixing in a single layer, we achieved the same results as processing the entire sequence at once. However, in a more complex architecture with multiple layers, the approximation introduced by a decay mixing becomes evident. To evaluate its performance, we conducted experiments on a dataset, dividing sequences into chunks and comparing different processing methods. The results showed that a decay mixing outperformed mean mixing and processing only a part of the sequence. Nevertheless, it fell short compared to processing the entire sequence, indicating that a decay mixing provides an approximate solution when dealing with stacked layers in RNNs.